So now we continue with the AI ML related presentations from this morning, and right now it will be Antonio here from Miteco that will provide us some context about the work that he's been doing with respect to real-time transcriptions and all the related work with that. So please, Antonio, the floor is yours.
Okay, just a second. I have to finish my presentation. Okay, can you all hear me fine, yeah? So, hello everyone. My name is Antonio, and in this presentation I'm going to talk about Whispy. Just to warn everyone here, this presentation is tagged as not safe for work, and this is just because there is a live demo going on, which I know it violates the only one rule about live presentations, which is just don't do them. But I just decided to YOLO into that and see what was happening, okay? So before we begin, I also wanted to thank everyone that attended. This is my first JanusCon, and I know for like lots of you, it's the second one. So this is a great event. So thanks everyone for being here. It's been really awesome so far. I've been having a blast, and I hope it's the same for you. Okay, all right. So hello, my name is Antonio. I am a machine learning engineer working at Miteco, and before that, I spent some time in Ireland, roughly like 10 years, where I got my PhD, and even before that, almost like a lifetime ago, I graduated here at the University of Naples under the wise supervision of Simon Pietro. So those were like nice times. Now, I'd like to start this presentation with a really sad story. So, as I told you, I spent some time in Ireland, and when I left, kind of like 1 year ago or something, I left my clicker there, and I used that clicker a lot, and it was really a nice clicker. Probably it was not like a Ferrari of clickers, but definitely like a Mercedes. Right? This was great. So I didn't really want to buy a new one, so I had to come up with a different contingency plan. So the plan was really easy and straightforward. I guess we can all agree on that. So the first step was to getting hired by a tech company, and that is done. The second step was to build a speech-to-text system for real-time or quasi-real-time audio, and that should be done. The third step was to design or like concoct some sort of a spaghetti code thingy to simulate mouse and keyboard events using voice, and that we will find out in a second if it's done. Then wait for JanusCon, and then finally present my stuff without the need to use my stupid fingers to trigger transitions. Also, we're Italians, so we need like our hands free when we present. There is an optional step there, which is like probably like fail terribly in front of everyone. So we're gonna see that in a second. And so pretty much this is where we are now, and today is the day. Things seems to be working here. So now I have a set of like super secret words, like unicorn, for example, that should trigger kind of like live captioning of whatever I'm saying. Now there is a number of other secret words, and I hope you will not scream these words to trigger transitions. For example, I can say pizza, and it should just keep going. As you can see, I'm still like waving my hands here. Now there might be like a little like tiny issue with like the visualization, but like again, we will find out. I don't know if maybe like the screen is a bit kind of like compressed. Anyway, I have like a number of other words. I can say pineapple. I know that Lorenzo will be triggered by that as well, not just my slides. But anyway, like for the sake of this presentation, I will also use my stupid fingers to like transition between slides, okay? So we will begin and we will see how this thing work, and we will pretty much delve like into the nitty-gritty details of how we did it. This is gonna be kind of like in detail presentation, so a bit different from all the high level things you've seen so far. All right, so this is probably not necessary, but like I wanted to give you like a brief overview of what speech to text is. So essentially, you just consume audio data that come from any source, and you use like voice content in that data to do a number of like, things with that. Like you do awesome things like a live transcription, just the thing that you're seeing now. You can do like translation. You can do voice activity detection, or you can identify the language that's being spoken. In particular, the model we are using at the moment is doing all these things, or like kind of all these things. Ideally, if I switch language, it should kind of like follow through. So se parlo in italiano, per esempio, mi dovrebbe dare un transcript che resta comunque coerente con quello che sto dicendo, più o meno. I don't know what that is. I'm not sure. Oh, thank you very much. Yes, that's way better. Okay. All right. So this is pretty much what we can do with these models, okay? Specifically within the speech-to-text realm, the Whisper family of models came out like not that long ago. It is a family of like pre-trained models that are powered by OpenAI. I don't think there is any need for any explanation there. They are trained on like a huge amount of like audio data. And at the moment, they represent the state of the art, at least for like zero-shot learning, which means they have like no kind of like specific purpose in mind, but pretty much they perform quite well. Now, Whisper models, they come in like several flavors. There are like lots of toppings for Whisper models. I think some have already been mentioned. So you get like a faster Whisper, you get distant Whisper, you get like Whisper timestamps, you name them anyway. Now, this is all cool and everything, but there are like a couple of catches there. So the first thing is that Whisper models, they are limited for offline use only. What this means is that you just need your entire audio content when you start inference with them. And also, just like any other like transformer models, they have the tendency to hallucinate, which I guess we can all agree it's fun, just not at inference time, right? So we don't want to do that in a sort of like a real-time scenario. Okay, so now we will see how we addressed these two issues with Whispy. And we're going to check some of the details and what we are planning to do to kind of like improve the techniques we have at the moment. So first of all, what is Whispy? So Whispy is essentially a transcription service. We made like a nice package out of it. It's kind of like self-contained, it's ready for production. So it's kind of easy, at least for us, it is like to like plug it into like pipelines of like real-time applications. It is based on a sort of like pipelining mechanism that can easily be extended for other types of AI-based applications. So at the moment, kind of like the consumer of whatever we are reading from the source is a Whisper model, but that model, like that intelligence, can be replaced with any other AI-based component. And yes, at the moment, it's pretty much incorporated into the Mythico suite. Okay, so the basic idea behind Whispy is kind of straightforward, I would say. So we did in like a streaming audio source from like any remote source. We buffer it in a kind of pre-configured way. Then we transcribe the chunks that we previously buffered. And then we kind of like want to clean up a bit the transcriptions that come out of the model. So we want to detect hallucinations. We want to kind of like check that everything is in order. And then we merge the transcriptions that we generate after like we filter out like overlapping parts. And we are going to see in a moment why this is needed. I am sorry. Yeah, so yeah, kind of, I guess, like this needs no further explanations. Okay, so the main ingredients of Whispy are just like four. So we have like a kind of an input stage, which is like a pipeline that is based on FFmpeg. We have shifting data register, a whisper model, of course, and then we have like two other components, which is like a filter for hallucinations and a generator of suggestions. Wait, did I mention anyway that like, yeah, these transcripts come from my environmental microphone, so the thing can be a bit confused because I think it's getting both my voice and my amplified voice. So yeah, just to mention that. Okay. Yes, anyway, like this is essentially kind of like a rough overview of what's going on with these transcriptions you are seeing right now. Also, like this demo is local on my computer. That's why I'm afraid it might explode like any moment. But anyway, yes. So what we do is pretty much we consume a Janus stream, we put it through our input pipeline, we buffer it. So like we kind of like chunk, we make like nice chunks out of the audio data, and then we transcribe them, we polish the transcriptions, and we kind of like send them to their final destination. Okay, so the input pipeline is based on FFmpeg, as I said. So what we do essentially is just consuming Janus remote RTP stream. And then what we do is with FFmpeg, we convert it into a local RTP stream after FFmpeg takes care of all the data manipulation and pre-processing that is needed to kind of like convert whatever audio we are consuming into a sort of like whisper-friendly format. So this way we kind of like demand all data manipulation to FFmpeg, and we just don't want to have anything to do with that. At least I don't want to. Also, like this is kind of like very flexible because it's very easy to extend this sort of architecture to a multi-session scenario. So maybe you have like several sources that you want to read at the same time, or you want to pretty much forward whatever comes out of this pipeline to several consumers, which might be like different data structures or AI components. So this is kind of nice. Then there is the data register. Data register doesn't really need much explanation. It's just like a FIFO queue. So what we do here is we configure this one when the service is created. Only things we need to know is the number of audio chunks we want to store, is the temporal duration of each chunk. So I think at the moment you are seeing like the demo should be like 3.5 seconds for each audio chunk that we process. And of course, the sampling rate of the source audio. Then you get like the maximum length, and using like these numbers, you can also store temporal coordinates. It's these like absolute coordinates. So when you start, when you ended, and pretty much the temporal frame of each individual chunk in the register. Then there is the transcriber, of course. So now transcriber is somehow agnostic to everything else that's happening outside in the service. It only requires like audio chunks. It kind of like crunches them and it produces the transcriptions. Now, because of like our structure, whatever is stored into the shifting register is already is like ready and polished and can be fed into Whisper model without anything else to do. There are two important things to notice about the transcription process, and we're going to see both of them in a second. So the first one is the retranscription policy. The second one is the kind of like silence detection. So when it comes to retranscription, we're going to see in a second, I don't really remember when because I don't have the next slide here. We're going to see that like in Whispy, there are like portions of audio that are transcribed more than once. This has like two main advantages. The first one is that even when you're experiencing delays in your network, so maybe like your source kind of like stutters a bit, or you have like issues within your service, so there is like a delay or like you stop for a moment, you're not gonna lose any data, any audio data, which means that like even if you skip one transcription, that audio will be transcribed in kind of like the next iteration. And this also helps with context. This happens when, for example, like you are chunking a sentence and there is a word that is cut like halfway between like one chunk and the next one. So this should kind of like help a bit with that. I mean, Whisper also has like inside mechanism to do that, but like we found that this works a bit better. The second one is like to filter out regions, silent regions. So it's like portions of audio where there is no voice activity, and this definitely helps with like speed. So talking about voice activity detection, so OpenAI people were like kind enough to embed voice activity filter inside Whisper. It's actually a different model. It's called Celero VAD. And what Celero does is essentially consume audio data. It consumes audio data and then just tells you, hey, nothing's happening from this timestamp to this other timestamp. So you can just ignore that when you're gonna transcribe your audio. So all we have to do in our scenario is pretty much save those time coordinates and just kind of like use them to kind of like nicely cut our audio data. This is an example. So in the top bar, you can see the content of like the audio buffer. There are like some regions which are voice and some regions which are silence. We store the coordinates of like the silent regions. And then whenever like a new chunk comes in, what you do is you dequeue the first chunk, you shift all the coordinates, and then you perform voice activity just on the new chunk. So this saves like some time. And in this particular example as well, what you can see is that there was a voice region that was cut kind of like halfway between like one chunk and the next one. So in this case, when you are retranscribing the entire buffer, after you excluded the silent regions, you might have like a better transcription of whatever you transcribed earlier. Okay, so this is like a broad overview of like the transcription algorithm. I mean, this is a pseudocode, but it's not really far from the real code because Python. So essentially, we take the last chunk, we run voice activity detection. If there is no activity, you can just as well flush the content of the entire buffer because it means there was like a significant pause. So it's really unlikely that like somebody stopped halfway through a word, I guess. Okay. And then you update your coordinates, you get like the speech content of the buffer, you transcribe, you filter out hallucinations, you generate the suggestion, and you're good to go. Okay, I also wanted to mention, like in this case, that we are using a version of Whisper that is called Faster Whisper. I think it's been mentioned before. This is essentially just like a quantized version of Whisper. So it's just the same model, kind of stripped down of whatever is not needed at inference time. So it's significantly smaller and faster than the original Whisper model. I think we are stuck like in version 0.10 or 0.11. We had like some issues with the latest one related to hallucinations. There were just like we were flooded with hallucinations and we just decided not for a live demo, like not in a million years. Okay, so when it comes to hallucination filter, there are like different kinds of hallucinations that you can get out of Whisper transcriptions. These two are kind of like the same one. So you might get like one word repeated over and over again, just like this example below there, or you might get like a sentence repeated over and over again. Now, when you get a sentence repetition, there might be like small changes between like one repetition and the other, often maybe related with like punctuation. So it's like very subtle. But essentially we decided like to treat these two kind of hallucinations differently. For the first one, it's kind of trivial. And at the moment we are working with a sort of like thresholding mechanism because we just assume like unless you are like Eminem, there is no way you can repeat like a word 20 times in like 3 seconds of speech. For the second one, we are using like a kind of like more complex approach using metrics profile. So metrics profile is a library for time series analysis. So it is really helpful to find out motives in a time series. You can get like the number of occurrences of a motif. You can also use it to get anomalies. If you don't know it, like check it out. It's kind of like very expensive when it comes to resources, but like in our case, because transcriptions are usually kind of like short, because like we are looking at like 3 to 5 seconds of audio, it is quite effective, and it has literally zero impact on the final transcription time. So it's like shooting a fly with a bazooka, but in this case, it's effective and cool as well. Okay, there is also a third type of like hallucinations, which I'll mention at the end, which is when Whisper just comes up with made up sentences. And that one is tricky because you have no reference, there is maybe no repetition, you have no way of knowing whether that sentence was uttered or not. But we are also working on a way to checking that using retranscriptions, but we'll see that at the end. Okay, so then when it comes to suggestion generation, now I want to like tell you why that's needed, and the main reason again is that because we are kind of like transcribing overlapping audios. So whenever like we get like the content of the buffer, we transcribe it. Whenever we get the next one, we essentially transcribe a good portion of it. So what happens is that we need to pretty much merge the two sentences that we got out of these two subsequent transcriptions. And to do so, we're using the Levenstein distance. So the Levenstein distance is just the edit distance. So essentially, we just use it to find kind of like the best cutting point between the previous text and the current text. So here is an example. I don't know if it's readable, probably not. But anyway, we have like the transcription on the previous text and the transcription on the current text, and there is like overlapping text between the two. So what we do is like we go backwards from the new one, and we keep adding words until we minimize the edit distance between the previous and the current. After we found that, after we managed to get that, we use that as a cutting point for the new transcription that has been generated, and we just then merge them. So it's really, yeah, it works for us. It works on my computer. So. Okay, anyway, now we have like all these things in place, but we were also interested in understanding where we stand compared to the offline Whisper. So how, like, are we getting penalized in terms of like transcription quality by this kind of like online mechanism? And in order to do so, we kind of evaluated some data sets in terms of word error rate, which is like the pretty much the de facto standard metric to evaluate transcription systems, and also time. So we want to know what's the kind of like delay that we introduced using using the whole shebang. So now here we have, okay, you can see the thing. So now we have like a comparison with the offline Whisper. Now on the x-axis, you have like data sets that are like, these are like commonly available data sets. In particular, well, I think this one, I'm not sure this one was included in the kind of Whisper training data set. Anyway, for like all of them, we just, of course, kept the test partitions, not the training data. And then on the y-axis, you have the word error rate. So as you can see, for pretty much all of them, so the word error rate of Whisper and the word error rate of Whispy pretty much fall into kind of like the same kind of like order. Essentially, what we are losing here compared to the offline transcription is around like 1 to 2%, which I mean is not bad. I mean, something's happening with the Rev 16. So Rev 16 was like a weird case. I think this was the longest. And I should also mention here that these results were obtained with a former version of Whisper, sorry, of Whispy, where the hallucination filter was not the one that I showed you right now. So these results here are caused by hallucinations, just by hallucinations, which is crazy because like here on average, we kind of lose like 5 to 7% compared with the offline transcription. Okay, so this one is just a kind of like a closer look at what we just saw. Essentially on the columns, we have like the model size. So it's like the large, medium, and I think this one is like the small and the base, like the other way around, I can't really read. And on the Y, we have the data sets. Now on the x-axis of each one of these scatter plots, you have the word error rate for Whisper, and on the y-axis, you have the word error rate for Whispy. So whenever there is a point that falls below the bisector of the quadrant, it means that Whispy is doing better than Whisper. Yes. And whenever like a point falls above the bisector, it means that Whisper is doing better than Whispy. So like for this case, we are kind of happy to see that there is this kind of nice clustering around the bisectors for like most of the data sets, which is it's nice for us to see. Yes. Okay, so now this is an analysis of, and again, also these numbers, like these plots were obtained with the previous version of Wizard. It's exactly the same issue that we had with the other plot. Then when it comes to transcription delay, we were interested again in kind of like understanding what sort of delay we are adding to the whole pipeline. Because of course, if you want to transcribe, let's say, audio in like chunked into like 3 seconds, you gotta wait for 3 seconds, right? Which, I mean, in our scenario kind of works really, really fine. But then we also want to know, okay, how much are we adding for the transcription and to generate the suggestion and to filter and to do this and to do that? Because if we are doubling that delay, then it's not nice. Now, again, these times that you see here are obtained with the first version of Whispy, where the voice activity detection part was not optimized. This means that we were pretty much running voice activity detection on the entire buffer in every iteration. So every time there was a new chunk coming in, then we would need to kind of do voice activity detection on the entire thing all over. After we removed that, from these numbers, we were able like to kind of like shave off like something in the ballpark of like 200 milliseconds or something. So we were getting something even nicer. And of course, we excluded like the ESIC dataset because ESIC dataset is gigantic, but it's also made of like very small audio clips, which means that we are getting like results that are too optimistic because there is like this ramp up phase where like you are filling in your buffer. And of course, you are transcribing buffer that is kind of like a buffer that is shorter compared to when the buffer is full, which will give you like a very kind of like short time for the transcription. But yeah, in general, these are the times we are looking at. So, and I think this was obtained on like a single Tesla T4 card, just so you know. But like the transcription you're seeing here are running on my laptop, which has like a 4050. It's like the same number of CUDA cores, but less VRAM. Okay, so just to kind of like close the entire thing, at this moment we have like a system that is fully operational. We are kind of integrating it into the Mythico suite. And of course, we are working on like our next steps. So the first thing is to work out like a way to filter all the hallucinations, even like sentences that are like completely made up. So we're working on a sort of system of confirmations. So what it means is that if I transcribe like an audio content that has an hallucination, that hallucination might appear only once. So when I transcribe like the shifted versions of like that buffer, that hallucination will disappear at some point. So if I confirm it and I say, okay, this appeared once in the transcription, in the next step, I say, this just disappeared. And in the next one, I said, still not here. So that thing is made up. And of course, we are also looking at like to improve like resource management and to add like some extensions. Because as I said, like this is a sort of flexible system. So whatever we are doing with the Whisper model at the moment can just be replaced with like another component that does like a different thing. So maybe we want to do summarization. So we want to take whatever has been transcribed up to that point, we want to kind of like feed it to a different AI model, and we want to get out the summary, or maybe we want to do diarization. So we want to understand who is who when multiple people are speaking, which might happen a lot in Italian conferences. And anyway, we have like a paper under review. So everything you've seen so far is under review at the moment for like the ECML PKDD conference that is going to be held, I think in September in Lithuania. So yeah, I guess that's it. And just to close it, I found the clicker at the end. So it was in my luggage and it was there all along. So this is pretty much all for nothing. But anyway, thank you very much for listening and for reading as well. If you have questions or comments, just hit me up.
Thank you, Antonio, and I'm glad you find your clicker. So happy ending. Any questions for? Okay.
Hi, a couple of questions. The first one is, Whisper doesn't support real-time transcription, right?
Yes.
So are you creating actual file chunks for every utterances?
No. Everything is kept in like memory.
So you kept in memory and you created separate. Okay.
Yeah. So we are actually keeping the waveform, like the raw waveform of the audio that we consume from the source.
Okay. And the second question is, I mean, if you had implemented the VAD and the Janus itself or the SFU, would it have been a better performance for?
And can you repeat? I didn't.
If you had implemented the voice activity detection and send just the chunks based on voice activity detection, would that have created a better performance?
Well, I think like if I got your question correctly, this is what we are doing at the moment. So if you look at this, so
at the Janus, not at the Celero,
Janus.
because you're taking care of you're taking advantage of Celero in the Whisper
yes.
stuff.
Oh, okay.
But
okay.
instead of that, have a pipeline on the Janus itself and send just the chunks.
So like at the source, you
At
mean?
the source.
Well, like the thing is that maybe you want to consume that source for, like with a different model that does like something else, doesn't really care about silence. So the idea would actually be to extend this pipeline and saying, okay, before feeding that to the model, I will have like another component that the only thing it does is voice activity detection.
Right. That's what I'm saying. Would it? My question is, would it improve your model, your latency, and all that?
So I don't think it would have any impact on the model performance in terms of word error rate.
Yeah.
And I guess the same goes for like latency. Probably not. Like it wouldn't have like an impact because like at the end of the day you are still doing voice activity detection on the same data. So now where you do it doesn't really change. I think the time you.
But the assumption if Celero is as good as your voice activity detection on.
Oh, we're using Celero.
Yeah, I know. Assuming if they're same good quality voice activity detection, then it will be the same performance.
Yeah, pretty much yes. Yeah.
Okay, thanks.
Thank you. We will definitely try this. You talked about diarization at the very end as a to-do.
Yep.
Don't you ingest individual streams already? And there we already have, in our case, it would be, we already would have the speakers diarized per stream.
No, like at this moment, we are not processing individual streams. Like the content we're getting is mixed. So if we want diarization, we need like to have like another AI component. Of course, because like we are having like Janus, the idea could also be if there is like any stream that is not already mixed, we could use that and we will get like diarization for free. Otherwise, the alternative is just like to feed, the output of the input pipeline into like a different model where you get like the mixed audio stream and then you get like the, timestamps of like speaker 1, speaker 2, and speaker n. I guess we do, right?
We don't mix audio streams.
Huh?
We don't mix audio streams.
He said that in Janus, if from Janus you are feeding separate streams, you can handle them separately and you get diarization for free, as you said. And he said, we ourselves in Miteco, we are using mixed streams in our room virtual event platform, which is why we need separate diarization for that. But yeah, if you feed, but you can, because if you're feeding separate streams, you just need separate pipelines, I guess. For
yeah, but also I guess like if you're feeding streams that are not mixed, you don't need diarization. Like you already have the information there. Yeah. Yeah, but like we want like a single stream, and then yeah, we want to like pour machine learning over that. Yeah. Okay.
Any other question over there?
Hey, thanks. Very interesting presentation. I probably missed it. So is it on GitHub right now?
No, not at the moment.
What's the plan for that, if anything?
I cannot confirm nor deny what's going to happen with this project and GitHub, but I guess at some point, like parts of these will be released, but I don't know. I guess maybe like better people are, yeah, they can give you better answers than mine.
No, as Antonio said, at a certain point it will happen, but there is work that needs to be done. There is, for instance, there's a whole container format that we want. So for instance, Antonio already anticipated some parts about the pipelining concept. We want to make this in a framework to make this better adaptable for different use cases rather than just transcription. So in this case, we have a specific use case. We want a framework that allows for different use cases beyond just transcriptions that may include video, may include other things and so on. So we are in the process of figuring out what it will look like. So releasing something now would be helpful on some aspects, less helpful than others. So we are figuring this out as we go, basically.
Yeah. This one is a transcript of the entire talk. Just
okay.
Fleshing that out.
Yeah. Any last question for Antonio? Okay, thank you
Cool.
very much.
Thank you very much.